Hi everyone, so this is the second part of the second lesson for Chapter 2. Continuing our study. Now I left you with this slide in Part 1. This is the last slide that we looked at. And so we're going to start here with ions, a quick sort of review here, because this is important in the first part of this lesson. So remember that ions have an unequal number of electrons. So if you have an atom that has a net negative charge, that's an ion, or a net positive charge, that's an ion. So in other words, the number of electrons does not equal the number of protons. So there's a net electrical charge, and you'll recall that we used the word cation to describe an atom that has lost an electron. So because it has lost an electron, that means it's more and more positive or less and less negative. It doesn't, you can look at it both ways or one way or the other. I know how I look at it, and I'll go back and forth. It's something that you're going to have to work out in your own mind how you want to remember it. But cations have lost an electron, and as a result they become more and more positive, so they have a net positive charge. The examples that I gave you then were calcium with its plus, and this plus stands for +1 because it could have more than one positive charges. Sodium with its little plus there, +1, and potassium. These are all atoms that you'll become very familiar with in your study of biochemistry or biochemical reactions. Okay, so an anion then has gained an electron, and therefore it has a net negative charge. All right, so cations become more positive, anions become more negative. And my examples here are chlorine with its little negative charge and oxygen with its little negative charge. And I think this will all become more clear momentarily. So we have cations and we have anions. Cations have a net positive charge, anions have a net negative charge. And I liken the cation-anion idea to a battery. You're all familiar with batteries, with one end is positive and the other end is negative, and that's really what's going on here. So we have a net positive charge over here, net negative charge over here, and so the positive end of a battery is called the cathode. That's the cation side, and the negative end of the battery is called the anode, or the anion side. Okay, I don't know if that image makes it more clearer for you in your mind, but that's the way that works. So we have the cation side and the anion side, or the cathode anode. Now, ionization is a process where we take a neutral atom and we turn it into a cation or an anion. We either make it more positive or more negative, and here's how that works. Here is calcium, the element calcium, with its atomic symbol here, capital C, lowercase a. The 20 up here represents what? Represents the atomic number, so that's the number of protons, positive charge. And so by definition, you know this is a neutral or balanced atom, so it must have the same number of electrons. So that means it has 20 electrons as well. So the 20 positives cancel out the 20 negatives, and you have a zero net charge for calcium. Now, we want to make a cation. We want to turn calcium, we want to make this atom more positive, right? In order to make a cation, you have to lose an electron because it has to become more positive. So we need to lose a negative charge. So we have 20 electrons here. You know, they're electrons because I have a little minus sign in parentheses. That's all that means. It just means these are 20 electrons. And we need to get rid of them, get rid of one, because we're making an anion. We're making an ion. We're making a cation, an atom with a positive charge. So we need to get rid of one electron. And so 20 minus 1 is 19, of course. 19 little electrons there. And then we're going to take our 20 protons with a little positive charge. We're going to subtract the number of electrons, 19 there. And that gives us 20 minus 19 is 1 net positive charge. And we denote that by writing the chemical symbol Ca, and this is on the right side, superscript, the little plus sign. You could also write this as a +1, because you can have a +2 and a +3 as well, but by convention, we know that when you write plus here, it means +1. It means 1 positive charge. So this is a cation, calcium with its positive charge there. We can take that a step further, right? So if we want to increase the positive charge on calcium, then we can remove another electron. So here's 20 electrons. We're going to get rid of 2. 20 minus 2 is 18. So 20 positive charges here minus your 18 negative charges gives us a +2. All right, so now we have calcium with a +2 charge, or 2+ charge. And we denote that by writing the chemical symbol Ca on the right side, superscript, ++. That means 2 positive charges. That means an ion with 2 extra positive charges. Or another way to write it would be the chemical symbol with a +2. Remember, if we just have the plus here, that by convention means +1. If we have anything greater than 1, we need to put the number there. All right, so this is calcium with a +2 charge. With a +2, that's positive charges, right? So on the flip side of the coin, we have, how do you make an anion? This is an atom with a negative charge, a net negative charge. Here we have chlorine with its atomic number 17, 70 protons. That means 17 electrons, and we're gonna pick up an electron, right? We're gonna make this thing more negative. We're making an anion, so we're gonna add an electron. 17 plus 1 is 18. So now you have one more electrons, and then you do protons, and so you take your minus 18, your 18 negative charges here, subtract your 17 positive charges. 18 minus 17 is 1, and of course that's a negative charge. And so we have chlorine, a chlorine ion. We have chlorine with a net negative charge. We denote that with the chemical symbol Cl. And right side superscript, the little minus sign. And by convention, we mean -1. Because we could have -2, -3, and so on. All right? So ions, once again, are formed when atoms lose or gain electrons. When an atom loses an electron, we call that a cation, becomes more and more positive, and we say that the atom has been oxidized. The process is called oxidation. And when an atom gains an electron, it becomes a more and more negative, right? We call that an anion. So I always remember this with the A. Anion means you're adding a charge, adding a negative charge. Okay, so we gain an electron, we become an anion, and the process, we say the atom has been reduced, and the process is called reduction. So in the little diagram down here, we see two atoms, and they're just floating around, and they become, they start to intermingle in the natural milieu. And so one atom here with an electron there, and this atom here needs an electron. That's what's going on here. So they're going to, so this atom is going to pass its electron over to this atom. So this atom loses its electron, therefore, or thereby becoming oxidized. This is a cation now. And this atom picks up that electron, or gains an electron, thereby becoming reduced. So this is an anion. Now in the natural world, in biochemical systems, oxidations and reductions always occur together. You can't just take an electron and throw it away, right? You got to have something there to pick up, otherwise you have electrons bouncing all over the place all the time. So when atoms in natural and biological systems interact with one another, one atom can, we say, donate its electron, and another atom will accept that electron. And so one atom becomes oxidized while its adjacent atom becomes reduced. And that happens in biological systems. Oxidations and reductions always occur together. Compounds in biological systems are formed when atoms share electrons. So one atom is oxidized, becoming more positive. The adjacent atom is reduced, thereby becoming more negative. Remember that opposites attract. So the cation, the positive one, joins the anion, and a compound is formed. We'll look at that. We'll look at the formation of compounds in a second. And so as one atom is oxidized, right? Oxidation occurs when an atom loses an electron. The other atom is reduced. Reduction occurs when an atom gains an electron. And compounds are formed when oxidation and reduction reactions occur together. We call them reduction oxidation reactions. It's weird because generally you see this as oxidation reduction reactions. When you see these in sources and they write it out, it always says oxidation reduction reactions. But it doesn't matter which order you present these. In this situation, we're saying reduction oxidation reactions always occur together. And instead of saying reduction oxidation, we just shorten it to, and we just say redox. So redox reactions are reduction oxidation reactions coupled together to form compounds. So that's an important distinction for you to make between reduction reactions and oxidation reactions, and you also need to remember that they occur together in the natural world in biological systems as redox reactions. Okay, so the essential elements of life, these are things that we run into in biological systems and organic systems predominantly. There are other things that come and go, but you're always going to see these essential elements. Essential elements have atomic numbers less than 21, and they have very low atomic masses. And look, 96% of all living matter is made up of carbon, hydrogen, oxygen, and nitrogen. We'll see some other things thrown in there for good measure from time to time, but by and large, when we talk about organic systems, which we're going to be talking about organic systems and organic molecules: carbon, hydrogen, oxygen, and nitrogen. Important for you to remember those. So isotopes then. Isotopes are elements with different numbers of neutrons. So we have ions with atoms with different number of electrons. Here, isotopes are atoms with different numbers of neutrons. Remember, neutron is the second party in the nucleus. We have the neutrons, the number of neutrons plus the number of protons equals the nucleus. And the mass of those together is the atomic mass. Now, when we talk about isotopes, we are changing the number of neutrons. And so we're making a heavier atom by adding a neutron. So the number of neutrons here does not equal the number of protons. And of course it affects the atomic mass, because atomic mass is the mass of neutrons plus protons. So most elements exist in nature as a mixture of isotopes. Now, when we think of the natural world, we generally think of neutral atoms, but really in the real world it jumps back and forth. And so you're going to have you'll have, for instance, a lighter carbon and a heavier carbon in there, and it'll jump back and forth, right? Remember, nothing in nature is ever static. When stasis occurs, that equals death. So nothing is ever stable. The pH of your blood is 7.3, 7.4, 7.2, 7.1, 7.4. It jumps back and forth. Your body is always trying to reach 0, or rather 7, always trying to reach 7, which is neutral, but it never really gets there. It might be a little bit. You might be 6.999 acidic, or you might be 7.999 basic. Okay, so it jumps around there a little bit. So my point there is most elements exist in nature as a mixture of isotopes. We never always have just carbon, just neutral carbon all the time. And so carbon has 3 naturally occurring isotopes. Remember, that's different numbers of neutrons. So, quote unquote, normal carbon has 6 protons and 6 neutrons. You know this. So it has an atomic mass of 12, and we can write that with the chemical symbol C on the left side, superscript 12. Now, you don't always see this when you're reading a source and it's talking about carbon and it's using the chemical symbol. You just see C, capital C. You don't see C superscript on the left 12, because it's understood that C means normal carbon or neutral carbon, or carbon with a 0 charge. Okay, so that's carbon 12. We call it quote unquote normal. Carbon 13, though, has 6 protons, right? Carbon has 6 protons, but we're talking about isotopes here. So then it has 1 more neutron. It has 7 neutrons. Right? Normal carbon has 6 neutrons. Carbon 13 has 7 neutrons. You add them together, the atomic mass is 13. And you denote that with the chemical symbol, capital C, on the left side, superscript 13. Or you could also write it like this. You could also write it like this, carbon 13. Carbon 13, we know now, has 6 protons, that's not going to change, and 7 neutrons. Or you could write it like this, carbon 13. Now, carbon 14, right, has 6 protons, that never changes, but we need to get up to atomic mass of 14, 8 neutrons. electrons. There it is, atomic mass 14. We denote that, chemical symbol C. On the left side, superscript 14. You can also write it as carbon 14 like this. Okay? Now, you're not unfamiliar with carbon 14 because you've heard of carbon dating somewhere along the way. You've heard of carbon dating, like when they dig up old bones or old dinosaur bones or whatever. They carbon date them. That's using carbon 14 for that process. So carbon 14 is quite unstable, breaks down, releases energy when it breaks down, and we call that radioactive decay. And so carbon 14 is used frequently in carbon dating or dating old stuff, because carbon 14 it breaks down, it decays in a very specific way, in a very specific time frame. And so this illustration just shows you the isotopes of carbon. There's carbon 12, 6 protons, 6 neutrons. There's carbon 13, 6 protons, 7 neutrons. In the nucleus, notice the number of electrons does not change here. 6, 6, 6. Oh, that's not a good number, is it? And carbon 14, 6 protons and 8 neutrons. Now, obviously, it should be obvious to you that if the atomic mass is the number of protons and the number of neutrons added together, that 12 is much lighter, chemically speaking, but atomically speaking as well. I mean, it really is. If you could weigh these on a little tiny atomic scale, 12 would be much lighter than 13 and much lighter than 14. Okay, these are heavier. Okay, so radioactive isotopes like carbon 14 are unstable, readily decay. They decay at a constant rate, which is measurable, quantifiable, and that's where carbon 14 dating comes in. So we call the decay rate the half-life. So the half-life is the time it takes for 1/2 of the isotopes in a sample to decay. So 1/2 the carbon 14 isotopes in a sample of ancient bone to decay. And because the half-life is constant and predictable, radioactive isotopes are useful in carbon dating, or determining the age of prehistoric artifacts. All right. Moving on, electron orbitals. Electrons determine the chemical behavior of atoms, namely the valence electrons, right? The electrons on the outer edge or the outer orbits or the outer shells, they determine the behavior of atoms. The ones that are close to the nucleus, that are held tight to the nucleus, are very, very stable. If you have loose electrons or an unequal number of electrons moving around, orbiting the nucleus, those are the ones that are more reactive. So remember that electrons travel around the nucleus like little tiny planets around the sun. An electron's path, so the electron's path of travel is called its orbital. Now there's a distinction to be made here, but is not completely definitive that you should remember the distinction, but I'll make the distinction here because you'll read about it. So an electron's orbital may bring it close to the nucleus or allow it to move far away from the nucleus. And so we see here, we see a little Bohr diagram. We call these orbitals, or we call them energy levels. And so we see energy level here represented by this dotted line. And then we see the energy level here represented by this solid line. And the energy level, or the energy level, see, I use the terms interchangeably, but they really shouldn't be. This is the energy level that's closest to the nucleus. That's what you see here. It's called level K, or energy level K. And then we'll have letter designations as we move out. K, L, M, N, so on. All right. So orbitals, okay, the path around the nucleus is an orbital, but there is a level of energy, or an energetic level, that's close to the nucleus, and the more electrons you have, you have other energetic levels or energy levels further away from the nucleus. Now, orbitals go around the nucleus. Okay, here's the distinction that I wanted to make, and that I don't want you to get confused on. Orbital is just a term that means an electron zooming around the nucleus like a planet. And these orbitals, you know, at one point an electron is zooming around, and at one point it can get close to the nucleus, and as it spins around it can move further away from the nucleus and then back close to the nucleus, back and forth like that. Okay, so electrons change orbitals. That's my point here. And like I say, the distinction is not critical that you remember it. Okay, so here we have the nucleus there. You have energy level K, which is close, is the first energy level closest to the nucleus, and as you move out, here's energy level L. All right. Here's the distinction, don't get confused. An orbital can only contain 2 electrons. Any orbital can only contain 2 electrons. However, an energy level can contain 2 or more. Well, it can contain 1 or more electrons. So energy level K, which is closest to the nucleus, can only contain 2 electrons. Okay, so back here, looking at the orbitals, it's the orbitals that make this structure three-dimensional, right? I remember I told you it was like a little ball with the electron, with the little cloud of electrons zooming around. It's the orbitals because the electrons move back and forth. They move close and they move far away, and they're in the middle, and they move like that back and forth. And so it appears on the subatomic level as a little blurry ball. An energy level the energy level K can only contain 2 electrons. Subsequent energy levels, as you move out, M, N, O, and so on, can contain a maximum of 8 electrons. That's important for you to remember. The first level K can only contain 2, no matter what atom you're talking about. Of course, with hydrogen, there's only 1 electron. So energy level K has only 1 electron. But when you move up to helium, energy level K for helium has 2 electrons, because helium only has 2 electrons. But when you move up to carbon, see, with 6 electrons, then you have 2 electrons in energy level K, and then the other 4 have to move out to energy level L. But still L can contain a maximum of 8. So energy levels. So the closer the electron shells to the nucleus, the lower the potential energy of those electrons. And you're familiar with the terms potential energy, kinetic energy, and we'll look at the potential energy here. I'll give you an illustration of that in a minute. But the closer the electron is to the nucleus, the less potential energy it has. Remember, I said that the valence electrons, the ones circling the nucleus far away, far out, those are the ones that are reactive. So in the case of the electron, and in the case of energy level K, it's like the moon and the earth, okay? It would take something really catastrophic, astronomically catastrophic, to knock the moon out of orbit around the earth. But when you talk about something like Jupiter, for instance, with many moons, I don't know how many moons Jupiter has, and Jupiter is a very large planet. However, the moons that are circling, that are orbiting furthest from the planet, are the ones that are easier to knock off. So energy level K, which is closest to the nucleus, has the lowest energy. It can only contain 2 electrons. Energy level L, which is the next highest energy level, can contain up to 8. Alright, so energy level K, this should say energy level L, because K is first, can only contain 2. This should say energy level L, and all subsequent energy levels follow the octet rule. Octet, by definition, means 8, a group of 8. And so other energy level L, M, and O, they can have a maximum of 8 electrons, or hold a maximum of 8 electrons. And when that shell is full, when you have 8 electrons out there, then we say that that energy shell or energy level is following or concurring with the octet rule. Alright? So what if you have 9 electrons? Right? So if you have, or rather, what if you have 11, sorry, what if you have 11 electrons? You put 2 in energy level K, you put 8 in energy level L, 8 plus 2 is 10, you still have 1 left over. So what do you do with it? It has to go in the next highest energy level, which is going to be M. And now in M, there's only going to be 1 electron, and that obviously is going to be the most, I think it should be obvious that that's going to be the most reactive. So atoms with electron shells are full are said to be inert or non-reactive. They're stable, non-reactive. So as the electrons get closer to the nucleus, they lose energy. And the reverse is true. As they move away from the nucleus, they gain potential energy. And in the natural world, when we're talking about these atoms and their electrons, the electrons move back and forth between energy levels. Nothing is stable, okay? They jump back and forth between energy levels. And so in the situation here, right, here's the nucleus there, as an electron moves further and further away. So here's K, L, M, N. As the electron moves further away from the nucleus, energy is absorbed, and the potential energy that this little electron has is greater than the energy it had when it was down here. And remember, electrons jump back and forth. So this little electron might go boop, 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 and then it might go boop, boop, and then jump back, and then jump in, and then jump. Okay, it's going to jump back and forth between these levels. Okay, just because we take a snapshot like here, and an electron is an energy level K, doesn't mean it always stays in K. It jumps back and forth between the levels. All of the electrons do, and so they're constantly gaining electron, losing electron. As they move closer to the nucleus, they're losing electron. As they move further out, they're gaining electron, gaining energy. Okay. So we call it potential energy because it potentially can react with an adjacent atom, with another atom that it comes into contact with. So as electrons climb away from the nucleus, remember that step stool diagram, right? As they bop up away from the nucleus, they gain potential energy. That is, they become potentially more reactive with an adjacent atom. And so when we talk about potential energy, it's like pushing a boulder up a hill, right? So at the top of the hill, this is my little illustration of potential energy. At the top of the hill, the boulder has a maximum potential energy, right? When the boulder is up here, it has the maximum potential for doing damage to something down below if you push the boulder over the cliff, right? So as the boulder rolls downhill, it loses energy until it reaches the bottom and stops, and then it has no energy. Potential energy is zero. All right? So potential energy at the top of the hill, greatest. So when we think about energy levels, potential energy of any electron is greater at the top of the hill. The top of the hill is energy level M or energy level N or energy level O. It's way out there, away from the nucleus. Okay, so valence electrons, you heard this term before in the first part. Valence electrons are those electrons which have the greatest potential energy. So electrons inhabiting the outermost energy level have the most potential energy and are most reactive. So when we talk about that atom that I use as an example with its 11 electrons, right? You have 2 in K, you have 8 in L. Those are extremely stable, but you have that one circling around in M. That is most reactive. That electron has the most potential energy. That electron is referred to as a valence electron. Valence electrons are responsible for the chemical behavior of atoms, right? It's the valence electrons, the ones that are circling way out there, far away from the nucleus. There's no, if you will, no gravitational pull towards the nucleus, right? They can be easily picked off. And it's those valence electrons of adjacent atoms that allow for the formation of molecules and compounds, which we'll see here in a little bit. So atoms with full valence shells are chemically inert. They're non-reactive. And examples that you've heard, of course, are helium, right? I mean, we fill balloons with helium, and we take them to parties, and then when things get slow at the parties, somebody opens up a helium balloon and inhales that stuff, and then we talk like one of the chipmunks. Right? That tells you how inert helium is. You can actually breathe it into your body and it will not hurt you. Deep sea divers, right, as they are coming up, or as they are going down, and both coming up, but they breathe a mixture of oxygen and helium. Have you ever watched the Discovery Channel or whatever, and you hear these deep sea divers down below and they're talking? They sound like one of the chipmunks down there. That's because they're breathing a mixture of helium and oxygen, because helium is inert. That's my whole point there. Okay, neon also inert, as is argon. You don't have to remember those, but just remember if any atom has a full valence shell, it is inert. Okay, so valence electrons. Atoms like nitrogen want to have full valence energy shells. So all atoms want to have full shells. All atoms want to be inert. All atoms want to be neutral. Right? Nobody wants to be unstable. And so in the case of helium, you have 2 electrons. And remember that energy level K can hold 2 electrons. So we have a full energy level around helium. Both electrons inhabit level K. So that makes helium inert or non-reactive. Now look at nitrogen over here, right? 7 protons. That means 7 electrons. Energy level K, we have our 2 electrons. Remember, that's the maximum number that K can hold. And then everything else moves out accordingly. And so 7 minus 2 is 5, so we have 5 to deal with. So there's 2, 3, 4, 5. You can tell the difference because the actual electron is a little solid circle here, a little solid ball. The other spot where an electron can be added onto, that's where you see the little circle there, the unfilled circle. Alright, so in level L, you have 2, 3, 4, 5. But remember, L can hold 8. It can hold up to 8. So there's room in nitrogen for 3 more electrons. And so as a result, these valence electrons, these 5 valence electrons, are reactive. They have potential energy. So we say that they're reactive because they can be knocked off and sent over to another atom. And nitrogen itself is reactive because it has room for 3 more electrons, so it can pick up 3 more. So for that reason, we say that nitrogen is reactive. All right, rules to remember. If you change the number of protons, you change elements. Carbon always has 6 protons, right? Oxygen always has 8 protons. So when you change the number of protons, you're going to a completely different atom, or element, as it were. Protons are responsible for the chemical identity of an atom. So carbon is carbon because it has 6 protons. Oxygen is oxygen because it has 8 protons. You can never have carbon with 8 protons. So if you change the number of neutrons, however, you have an isotope of the same element. Remember that you can add neutrons onto certain other elements. In the case of carbon, right? And when you do that, you're fiddling with the atomic mass. So carbon atomic mass 12, has 6 protons, 6 neutrons. Carbon with atomic mass 13 has 6 protons, 7 neutrons. Carbon with an atomic number 14 has 6 protons, that never changes, but 8 neutrons. Okay. So if you change the number of electrons, you have an ion, either cation with a positive charge or an anion with a negative charge of the same element. These valence electrons are responsible for the chemical behavior. So chemical identity comes from protons. Chemical behavior comes from valence electrons. Now, molecules are held together in a stable configuration. My example here is a molecule of oxygen. This is gaseous oxygen. All right, you never see just one oxygen molecule. Here it links up with another oxygen, and that's very stable for the two. A compound is a molecule containing atoms of more than one element. So in this case, we have a molecule of oxygen, same element. Here you have same atoms, or atoms of the same element rather. Here you have a compound. This is NaCl, or sodium chloride, in other words table salt. It's a molecule containing atoms of more than one element. So here you have sodium joined together with chlorine. So the atoms in a molecule are held together by chemical bonds. And when we talk about chemical bonds, we have to talk about ionic bonds, covalent bonds, and hydrogen bonds. So ionic bonds occur when ions, that's the ionic part, are attracted to one another. We'll see that with sodium chloride. Covalent bonds occur when atoms share electrons. Hydrogen bonds occur when molecules share hydrogen atoms. By strength, and we need to remember this, covalent bonds are the strongest, ionic bonds are next in line, hydrogen bonds are the weakest, and actually there are other types of bonds which we will get into later on. So ionic bonds occur when a cation is attracted to an anion. Remember, opposites attract. The plus atom and the minus atom attracted to one another by virtue of their opposite charges. An example is a sodium ion here with its little plus charge, and a chlorine atom here with its little negative charge. Opposites attract, and so they get together in the real world and they form sodium chloride. Sodium chloride is what you know as table salt. So sodium has an atomic number of 11, chlorine has an atomic number of 17. Okay, and so sodium donates its one valence electron, so it gets rid of its electron, becoming more positive, thereby becoming oxidized. Chlorine accepts its one electron, thereby becoming reduced. Okay, so check this out. So sodium has 11 electrons. That's 2 in K, that's 8 in L, that's 10. So it has that extra one that I was talking about before. So it has one valence electron and makes sodium very reactive. Chlorine has 17 electrons. That's 2 in K, that's 8 in L, that's 10. That's going to mean there's 7 in M, and that means it has a space, right? Because it can hold up to 8 in that outer shell. So it has space for one more. This has one reactive electron. This has space for another electron. So you can see how they would join together. One becomes oxidized, one becomes reduced. That's the redox component of this. And you have sodium chloride forms as a result. And here I made a note, it's the electrostatic forces that hold the two together. It just so happens, you don't have to remember this, sodium chloride is held together in a lattice, so that if you look at this on the subatomic scale, but even you can see this to a degree, right? You pour some table salt out on the table, and it's little crystals. So the ionic bonds form crystals. That's the lattice we're talking about here. You don't have to remember that, but just for your information. All right, so ionic bonds here. Here's sodium chloride. I'm sort of going to rush through here because I don't want this to run too long. This just shows you sodium donating its electron and chloride accepting its electron to fill its outer shell to become stable. Sodium here gets rid of its one valence electron, thereby becoming stable. And so you have this crystal lattice that we call sodium chloride. All right, covalent bonds occur when atoms share valence electrons. They can be shared equally or unequally. If they're shared equally, we call that a nonpolar situation. If they're shared unequally, and we'll see this with water, we call that a polar covalent situation. The term here is electronegativity, and it's the affinity of an atom for an electron. So if an atom is largely positive and it has a strong draw of negative electrons to it, we call that electronegativity, and it is quantifiable. Covalent bonds are the strongest, and there are different types. We have single covalent bonds, double, and triple. single covalent bonds where atoms share one pair of electrons, double covalent bonds where atoms share two pairs of electrons, and then you have triple covalent bonds where atoms share three pairs of electrons. When we have a single bond, we just call it carbon-carbon bond. When we have a double covalent bond, we just call it a double bond. It's understood that it's covalent, a strong bond. And then we have a triple covalent bond, we just say triple bond. And we'll look at some examples with that. It says video here, and there's a little video that I want to show you, and I'm definitely running long here. So I'm going to stop here, and then I'm going to do another presentation for part 3 of chapter 2, and I'll post that sometime tomorrow. Okay, so we'll see you in the next one.